All right, good morning. I hope you all had a nice weekend. Are there any questions? All right. So today we are going to go back to the syntax of the propositional logic. We talked about the semantics in a sense that we defined what does it mean for a set of formulas or hypotheses, as we call them, to imply a proposition, a formula. Or what does it mean for two formulas to be tautologically equivalent? And as I pointed out a few times, and as you noticed, writing the truth table is a very bad idea. Even the shortcuts that we take with the states, essentially, there's no effective algorithm or way to decide whether a bunch of hypotheses tautologically imply a conclusion. That's why early on in the days of logic in the late 19th century, early 20th century, people decided to axiomatize to see if they can prove logical statements as opposed to checking the truth values. So they developed systems of proofs. And so the point is, yes, there is no effective way to check the truth table. So what if we invent a system of proof a proof system such that if I have a set of formulas gamma proves a formula A if and only if gamma tautologically implies A. So that's the whole point. Instead of dealing with the states, the truth table, and so on, find a proof system that does the job for you. And if you can prove something using a bunch of hypotheses, then it tautologically implies, right? And this is what we are going to do, to introduce a proof system that does this job. And our proof system, that means we are going to prove theorems, as we call them, based on the hypothesis from gamma in a system that is basically based on a bunch of axioms and rules of inference. So first of all, talking about axioms are clear. Well, they're going to be, well, they're not clear now, but they're going to be a bunch of tautologies that we're going to use. Those are the selected tautologies that are the most useful, and we're going to take enough of them. But what are the rules of inference? Rules of inference are also based on tautologies. So they tell you that if you have a bunch of premises or hypotheses, you can conclude a statement. So here, the way that we write them, we write these. So this is the sort of notation that is used for rules of inference. And this fraction tells us that if you have hypothesis A1, A2, AN, then you can conclude Q. So you have rules of inference before, like modus ponens, right? And modus ponens tells you that if you have A and A implies B, then you can conclude B. And these are similar. We're going to have rules of inference similar to modus ponens, but this is essentially same as saying that A1 and A2 and AN implies Q is a tautology. right? So these two are the same thing. By this notation, we mean this. This is notice that if all the AIs are true, then Q is true. So we can conclude Q from A1, AN. So what are the rules of inference that we are going to take here? We are not going to take model exponents. If we could have, in fact, in some other textbooks, they might take model exponents and maybe another rule of inference as our base to work with, as our primary rules of inference. But here we're going to take two different ones. That doesn't mean that our logic is going to be any different. We're going to produce the same logic, same equivalent logic. So whatever we can prove in one, we can prove in the other one, and vice versa. So our rules of inference, there are two of them. The first one is called the Leibniz rule. Leibniz rule tells us that if we have A is equivalent to B, so this is the hypothesis. If A is equivalent to B, then in any formula C, and remember this notation, let me remind you the notation that we defined last time. This notation is the formula that you obtain when you substitute P with A inside the formula C. And last time we proved that the result of this is going to be, again, a formula, right? So what is this saying? It says that if A and B are equivalent, then in any formula C and for any variable P, if you substitute P with A or B, the resulting formulas are equivalent, right? And this makes sense. Think of equivalent formulas as formulas that are basically the same, right? They're telling you the same thing. You kind of think that they are identical. And this is saying that if A and B are identical, then if you plug in A or B in two formulas for the same variable, you're going to get identical formulas. In this case, by identical, I meant tautological, well, the equivalent formulas, or tautologically equivalent formulas. So if you have A is equivalent to B, then you can conclude this formula. Note that this uses one hypothesis and gives you this formula. Now, the other rule of inference is called the equanimity law or rule. And here I have two hypotheses. It tells me that if I have the formula A and I know A is equivalent to B, then I can conclude B. Yes? If A and B are equivalent, yes. Yeah. That's what it essentially says, but you have to do the substitution in both sides. So if you have A and A equivalent to B, then you can conclude B, which is again sort of obvious, right? If you have A and A is equivalent to B, then you have B. So we only have these two rules of inference. Now, few remarks about the rules of inference. First of all, these are what we call schemata in general, meaning they do not apply for any particular A, B, C, or the variable P. They apply for any A, any B, any variable P, any formula C, right? So as we're going to talk about instances of these rules or laws when we plug in actual formulas, right? So for example, equanimity law, I could apply it to the formula P, and well, maybe P is a bad one. Let's say Yeah, okay. I need to come up with one that is of the form. Suppose you have formula A and um, P and Q and P and Q is equivalent to negation of P or negation of Q, right? I wrote this. Suppose we have these two, then I can conclude negation of P or negation of Q, right? Uh, but this was kind of obvious because I wrote De Morgan here, but this is in general, if I have any formula B that is equivalent to it, then I can conclude B. So these are not for specific formulas, they're for any ABC, and we are going to use instances of these. These are the what we call primary rules of inference. Along the way, we'll develop some secondary rules of inference that we might use, like the mod exponents and etc. But these two are the official rules of inference. So those are the rules of inference. How about our axioms? We're going to take the following formulas as our axioms. Suppose A, B, C are formulas. Again, this is not talking about any specific formula. A has nothing to do with letters A, B, C. It's about a general schemata of these axioms. The first one is the associativity of the equivalence, which essentially says the operation of equivalence is associative, meaning that if you have the formula here, this formula, which says A is equivalent to B is equivalent to C, right? So this operation A equivalent to B gives you a formula which is equivalent to C. This formula is equivalent to A is equivalent to the formula B is equivalent to C, right? That means if you applied the operation, this one first, A is equivalent to B first, and then took the equivalence with the formula C is equivalent, right? So think of this as the same as, if you apply the operation between B and C first, and you found the formula B is equivalent to C, and then took the equivalence with A. So the operation of equivalence is an associative one. The symmetry of equivalence is another axiom, which tells you that the formula A is equivalent to B is equivalent to the formula B is equivalent to A. Right? So we could swap the equivalence. Next one, top versus bottom. So this is going to tell us how top and bottom are related to one another. Top equivalent to bottom is equivalent to bottom, right? Again, think of these as tautologies that are basically trivial true. All of these are tautologies for any formula that you plug in for A, B, C, or whatever symbol there is. But in this case, there are no particular formulas. We're talking strictly about top or bottom. And what is the value of truth value of top is equivalent to bottom? Supposed to be false, right? Top is not equivalent to bottom. That's why it's equivalent to bottom, right? So that this is really a tautology. But again, these are based on tautology. These are in fact tautologies. But for now, at this point, we're only thinking about these in a syntactical way, right? So we're just going to assume our proof writing is really going to be purely syntactical without thinking about the semantics or whether these are true or false. But obviously, you want to have the system that doesn't prove anything false. So these must be tautologies. The next one, introduction of bottom. What does it say? It says that the formula negation of bottom equivalent to bottom, that has to be false, right? That's why it's equivalent to bottom. That's why negation of bottom equivalent to bottom is equivalent to bottom. Sorry, negation of A equivalent to A is equivalent to bottom. Associativity of the disjunction. So we have the similar associativity for disjunction that we said A or B or C is same as A or B or C, right? So again, it doesn't matter if you do this operation between A or B first, and then do disjunction with C, or first take this disjunction of B or C and then take the disjunction with A. Symmetry of or is symmetric. A or B is equivalent to B or A. Idempotency of or A is equivalent to A. Now, distributivity of or over equivalence or by implication. So if you have the formula A or B equivalent to C, then you can distribute. It's equivalent to A or B equivalent to A or C. That's why this is always a tautology. Any of these, if you don't think they're tautology, you could check the truth tables, and then you'll be convinced that these are tautologies. Excluded middle is this, that the formula A or negation of A. This is a tautology, right? So for any formula A or negation of A, it's a tautology, and we're going to have this as an axiom. Golden rule. Here, for us, the golden rule here is going to refer to the following tautology or following formula. A or B equivalent to A is equivalent to B equivalent to A or, sorry, A and B equivalent to A is equivalent to B is equivalent to A or B. Now, this is not that obvious, right? The other ones were pretty much obvious, but this is kind of difficult to imagine why such a thing should be a tautology for any formula A or B. But think of it this way. Let me reshuffle this a little and write it as, because I know I can reshuffle because equivalence is symmetric and associative. So using those two, I could reshuffle this and write it as equivalent A or B equivalent to A or B. So using symmetry, take this here, take this one here, or doesn't matter, you get this. Now this is more understandable if you think of it this way. By associativity, I applied associativity and symmetry a few times, and I get this thing, which is equivalent to the golden rule. But this says that A and B is equivalent to A or B. This obviously, this shouldn't be true, right? A and B is not same as A or B, but it is if and only if A and B are the same thing. So the statement that A and B is equivalent to A or B is same as saying that A is same as B. Right? Now this is understandable, and we can just really accept this. A and B is equivalent to A or B if and only if A and B are equivalent. Now, the last one, the implication or introduction of the implication symbol, tells us that A implies B is equivalent to A, or B is equivalent to B. Now, this is, again, it's not completely obvious, but this can be checked using a truth table that really A implies B and A or B is equivalent to B. They have the same truth table because this is always true unless B is true. Sorry, unless A is true, B is false. The same here. A or B equivalent to B is only false if A is true and B is false. All right. These, I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 axioms. The 11 tautologies are going to be our axioms. And then we have these two rules of inferences, equanimity and Leibniz. And these are going to give us a system for the proof. These are the bases of our proof system. But again, a few comments about this. Axioms are selected tautologies. We could have taken different set of axioms and obtained an equivalent logic, but they're not arbitrary. You cannot just take, well, I want to take this tautology, and this one. Now I have a similar proof system. That's not how it works. The proof system should be a complete one. Now these are enough axioms to prove everything that we want, everything that is true. And they're selected very, very carefully, but that doesn't mean there's the unique way to do it. It's the only way to do it. There are many other different set of axioms that we could take. In fact, if you open any two different logic books, they will take two different sets of axioms and do this, or even different rules of inference. But essentially, at the end of the day, that these logics are going to be equivalent, meaning they can prove and disprove the same formulas. The other thing is that these are also schemata. The schemata refers to, these are basically the template of the formula. That means they're not specifically for A, B, or C. They apply to any formula that you plug in for A, B, or C. So for example, if I replace here P is equivalent to P, or Q is equivalent to bottom, this is equivalent to P is equivalent to P or Q, or equivalent to bottom, right? This is associativity. This is equivalent to this. I just picked 3 random formulas instead of my ABC. And say the same is true for any other of these tautologies. For example, here, the excluded middle, I know that P or negation of P is an axiom. Because now we talked about the instance of this excluded middle, where the formula A is P. Again, take anything else, any other formula instead of P. Plug in for A. So, in fact, we have infinitely many axioms, right? They're in form of 11 schematas, but each represent, perhaps except this one. This one is really a single formula, but all the other ones represent infinitely many formulas. Any questions? So here I have another example, this formula that says P or negation of Q or P or negation of Q is equivalent to P or negation of Q. This is an axiom because it's an instance of the idempotency of this junction, right? So we're going to talk about the instances. All the instances of these axioms are going to be axioms. We're going to denote the set of all logical axioms, meaning the set of all these schemata and their instances. That means the set of all those infinitely many formulas with the letter lambda. So lambda is the set of all axioms. Now, another important notion, and this is the first notion that we need towards building our proof system. So what do we mean by a proof? What is a proof? A proof or a theorem calculation is defined as follows. Suppose gamma is a set of formulas. Now, a theorem calculation from gamma, or as we call it, a proof from gamma, or even simpler, a gamma proof, is a finite ordered sequence of formulas such that we can write following the two steps given here. The first step tells me that at any step, I can write a member of lambda or gamma. So again, let's go back. A proof is a sequence of formulas. It is finite. That means, so here I can write A, B, C, so on. And somewhere you stop, right? So for example, at the letter G, I stop. It's ordered, meaning the order matters. Now, also I cannot write these randomly. At any step, I can write an axiom, a member of lambda. At any step, I can write an axiom. Or a member of gamma. The members of gamma are called hypotheses. So those are the formulas that we are going to assume they are true. So a gamma proof is a proof using hypothesis, using members of gamma as hypotheses. So we're going to assume they are true. That's why we can write them. Axioms are tautologies. They are true. That's why we can also write them. So that doesn't contradict. That doesn't produce anything contradictory. So at any step, I can write an axiom. I can write an axiom here, but maybe at the second step, I wrote a hypothesis. A hypothesis means a member of gamma. So here, this would be a member of gamma. This would be a member of lambda. This would be a member of lambda, and so on. So this is the first restriction, first law. The second one is, we can remember we had two rules of inference, Leibniz and equanimity. Let me bring them up here. If we have written then top of the fraction, the numerator, then we can write the bottom. So that means in the case of Leibniz, if A is equivalent to B is written, then for any C, any variable P, I can write this formula. but only if A is equivalent to B is already in my proof, that is a member of the sequence. Then I can write the denominator. And in the case of equanimity, if for some A and B, both A and A equivalent to B are written already in the sequence, they're members of the gamma proof, then I can write B. So what's a gamma proof again? A gamma proof is a sequence of formulas such that at any step I can write an axiom, that means an instance of axiom, or a hypothesis, that means a member of gamma. And if the numerators of my rules of Leibniz, one of them is written, then I can write the denominator. You cannot violate these two conditions when you write a proof. Otherwise, that's not a proof. So this is usually what we call a formal proof, because it's within logic and it's written in very restricted way. But we're going to have some instances. So first of all, as I mentioned, this is purely syntactical. We're not paying so much attention at this point to the semantics, even though it must coincide with the semantics. It should not, you should not be able to prove any non-true statements or any contradictions. And this is going to be guaranteed, but at this point we don't know why this is guaranteed. And that's because our rules of inference and axioms, they do not contradict each other. They're all tautologies. But someone has checked that before. So we are just taking it for granted. Formulas in gamma, as I mentioned, they're called premises or hypotheses, or sometimes non-logical axioms. I'm usually going to use the word hypothesis or premises. Premises. And the other remark that I want to make, a gamma proof is finite. It has to stop at some point. It's a finite sequence of formulas. Now, here's the notation that we are going to use. Any formula, so suppose I wrote a gamma proof. That means that a finite ordered sequence of formulas that I've written respecting these two steps. Now, any formula that appears here in a gamma proof is called a gamma theorem. Any formula. So if there's a formula B here, I call B a gamma theorem. That means B is proved using the hypothesis from gamma. And there's a notation for it. So if A is a gamma theorem, meaning it appears in a gamma proof, we denote it by this. And we read this as gamma proves A. Or you could also say A is a gamma theorem. Now, sometimes we have hypotheses when we want to prove things. Really, a hypothesis is a set of formulas, right? It could be, I don't know, you have P, you assume P, you assume A, you assume A or B. Here I have three hypotheses. It's any set of formulas. Sometimes it could be empty. That means I have no hypothesis. In this case, if A, note that if I have no hypothesis, that doesn't mean I cannot write gamma proofs. I can write gamma proofs where gamma is the empty set. We call them absolute theorems, meaning they're proved using no hypothesis. Note that I can still, with no hypothesis, write axioms. Right? If A was an axiom, A itself is not an axiom, but if A is the formula that represents an axiom, for example, P or P equivalent to P, I can write it, right? At any step, you may write an axiom. Or I could write negation of P or P. And then I can conclude more and more using my rules of inference. So you can actually compute a lot of things. You can prove a lot of things, or not prove a lot of theorems with no hypothesis. And those are what we call absolute theorems, or sometimes they're called logical theorems, or just simply theorems. So A is an absolute theorem if the empty set proves A. Now, usually, if A is an absolute theorem, we don't write the empty set, and we just write this. So this means I don't have, on the hypothesis sides of this proof, I don't have anything. Yes?
If you're working with no hypothesis and you're just working with the axiom,
Yeah.
what's the point of doing modifying it if you know that the work is just
Yeah, but you want to prove tautologies. Yeah, so for example, we have all learned that, for example, we have a De Morgan law like this, that negation of P or Q is equivalent to negation of P or negation of Q. Like, this is what we called De Morgan in the past. And it's a tautology. But how do I prove it? That means I should be able to prove this with no hypothesis. I don't need a hypothesis to prove this statement, this formula. But it's not an axiom. So I cannot just write it in the first step, just saying, I put it in the first step, it's an axiom. It's not an axiom. We didn't take it to be an axiom. Axioms are selective tautologies. We didn't take De Morgan to be one of them. But that doesn't mean De Morgan cannot be proved. It can be proved, and we are going to learn how to prove De Morgan using write a proof for De Morgan or other tautologies. Yes? All the axioms are absolute theorems. Yes. That is a correct statement. Why? Because I can write them in the first step. Step one, write the axiom. You're going to have a proof using one step. Write the axiom. Now, also note that if I have a set of hypotheses called gamma, all the members of gamma, every formula that is in gamma, meaning all the hypotheses, are also gamma theorems. Because at any step, I may write down a member of gamma. So if A belongs to gamma, I write a sequence. At the first step, I write A. This is a gamma proof for A. Therefore, A is a gamma theorem. Now, let's give an inductive or recursive definition. By the way, when I say inductive definition, by the word inductive and recursive are the same thing. They usually refer to the same thing. So it's a recursive definition of a gamma theorem. So we just wrote the definition, and this is an equivalent way of defining a gamma proof. Suppose again, gamma is a fixed set of hypotheses. This is the basis of, or the basic step of the recursive proof. Any recursive proof starts with the basis step. Any formula in gamma union lambda is a gamma theorem. So we are defining the set of all gamma theorems inductively. In the base step, we say any hypothesis that is a member of gamma or any axiom is a gamma theorem. Why are they gamma theorems? Because there's a one-step proof for it. You can just write them down. Now the recursive step or steps, here I have two of them. The recursive step refers to the next two. Now, these two, the first one is regarding the Leibniz rule, and the second one is regarding the equanimity rule. So if A equivalent to B is a gamma theorem, meaning I could write it in a finite sequence, but we are assuming that it's already, there's a proof for it, meaning there is a sequence that A equivalent to B appears there. Then this formula for any C, for any variable P, is a gamma theorem. So this is again, it's a recursive step, right? So you're assuming that something is a gamma theorem, and now you're defining more gamma theorem. If A is equivalent to B is a gamma theorem, then for any formula C, if you plug in A instead of P, and then you plug in B instead of P, these are equivalent. So this formula that tells you that these are equivalent is a gamma theorem. Now the next step, if both A and A equivalent to B are gamma theorems, then B is a gamma theorem. Yes.
So if I have A, B, my theorem, I can use that other formula.
Well, if you know that both of these are gamma theorems. Oh, number 2. So if you know, so suppose you have a gamma proof, right? Meaning A equivalent to B is a gamma theorem. That means there's a gamma proof for it. So it appears in a gamma proof. Then for any formula C, this is a gamma theorem. So I can write it down. And this is same as the original definition that we just had, right? Because it tells you the same thing that here I said it in terms of if what you can write in a sequence, but this says the same thing. This identifies gamma theorems recursively. So here are 2 exercises. Show that if A belongs to gamma, then gamma proves A. I already mentioned that. What does this mean? This is just for you to practice to see if you understood these definitions. What does it mean, this symbol? It means gamma proves A. What does that mean? It means that A is a gamma theorem. What does it mean that A is a gamma theorem? A gamma theorem, they are defined, they are here recursively, and I see that at any step, I see it in step 1, that members of gamma are gamma theorems. So A is a member of gamma, therefore it's a gamma theorem. Or again, if you wanted to give a proof for it, now let's prove it. Step 1, I can write any hypothesis or axiom. A is a hypothesis. I wrote it. I don't need more steps. I'm done. There's a one-step proof for any formula in the hypothesis. Similarly, any axiom is a gamma theorem. But even so, any axiom is a gamma theorem. Let me add this one as well. If A is an axiom, that means A belongs to lambda, then gamma, for any gamma, it proves A. For any set of formulas gamma. When I say for any gamma, gamma could be the empty set. It doesn't matter because I can write a gamma proof for an axiom in one step. At any step, I can write an axiom. So if A is an axiom, there, I wrote a proof for it, just with this. So at any step, I can write, for example, this, because I know it's an axiom. So, example, P or P equivalent to P is an axiom. Therefore, it's an absolute theorem. All right, here, the next remark is just about how you read things, because I've seen so many times that students make mistakes with it. It's completely understandable in the beginning when you get used to this, but you have to avoid mistakes. And that requires you to understand the definitions. Here, really, the key point is understanding the definitions of gamma proof, gamma theorem. Don't mix them up. A gamma proof is a sequence of formulas. A gamma theorem is a single formula. And this notation here, it says A is a gamma theorem. And I've seen it many times that people say this is a gamma theorem. Then this says that gamma proves A. That's not the whole thing. This is saying that A is a gamma theorem. And these kind of mistakes that appear. This symbol, by the way, this whole notation and terminology, we didn't have in our alphabet, right? Or when we introduced the alphabet of propositional logic. So this comes from the meta theory. It's like when we're analyzing our logic, this is just simple fact that there is a gamma proof for A. Which is denoted by this notation. Yes. Gamma proofs contain all gamma theorems and nothing else. Yes. All right. So Now we want to write proofs. I just wrote trivial proofs in form of just one. If you have axiom or hypothesis, you just write the formula, which is either axiom or hypothesis. But usually, I mean, in non-trivial cases, we want to prove things that are non-trivial. In this case, like I gave you that example of De Morgan. De Morgan, I don't know how to prove it yet, because, or the proof is not trivial for De Morgan because it's not an axiom. And if it's not given as a hypothesis, and if I want to prove it as an absolute theorem, which it is an absolute theorem, then I need to be able to write a proof for it. And now there's different styles of writing proof. Again, remind you that the gamma proof is a sequence. It's a finite sequence of formulas, but usually we don't write sequences like this, gamma proofs like this. What we do is we write them in an understandable way that people can actually read it and understand each step. How did we get to the next step? That's why we usually, first of all, enumerate them. So at step 1, I write a formula. So we write them vertically as opposed to horizontally like this. So if this is the formula, step 1, and so on, I write it here. And then here I annotate. How did I get it? Was it an axiom? If it was an axiom, then I write an axiom. And sometimes I'll tell you which axiom as well. If it was a hypothesis, then I say it's a hypothesis. And step 2, I do the same thing. I annotate how I got it. Step 3, same thing. And finally, if you write a proof like this is called the Hilbert style of writing proofs, named after the famous mathematician David Hilbert. It's important to enumerate your sequence because we want to refer to them in our annotation. And it's also important to annotate. And this is similar when you write an algorithm, right? Similar to when you want to read an algorithm for the first time, you want it to be annotated so that you know what each step of the algorithm does. And this is exactly very syntactical. The whole point of writing a proof system is doing it in a way that it can be purely mechanical, right? As opposed to the tautological equivalence that we don't have an algorithm or a mechanical way of doing it. This has to be mechanical. So let's write proofs finally. So we're going to start with very easy proofs. Our first proof is it has 2 hypotheses. So in this case, my gamma contains 2 formulas, A, and A is equivalent to B. And then we want to show that gamma proves A, sorry, B. Gamma does prove A, but it also proves B. Note that instead of writing this, which is gamma, usually when you have finitely many hypotheses, note that nobody said that gamma should be a finite set. You could have infinitely many hypotheses. But when it's a finite set, usually we do not write the brackets. Just we understand here A and A equivalent to B are the 2 hypotheses that we have. Now let's start writing a proof in a Hilbert style. That means that each step you're going to annotate. Step 1, you have to start from somewhere. The first step, you have to write either an axiom or a hypothesis. There is no other way. Because you cannot yet use rules of inference. Here, I write a hypothesis, A. Why can I write A? At any step, you may write a hypothesis in a gamma proof. Right? Step one, I write hypothesis. I haven't violated, I followed the steps. I can write A because it's a hypothesis, and at any step, we may write a hypothesis. Let me annotate. The second step, I write our second hypothesis. Again, at any step, we may write a hypothesis. Annotate. It's a hypothesis. Step three, I'm using the second step. Here it said that at any, let me go back to definition of a gamma proof. At, was it this? Yes. If the numerators of the instances of rules of Leibniz, rules of Leibniz or equanimity are written, then you may write down the conclusion. If the numerator, here I have the rule of inference that tells me that if A and A equivalent to B, then I can conclude B. I've written both formulas in the numerator. Then we can write the denominator, B. So this is a gamma proof where gamma is this set for the formula B. This is basically the equanimity. By the way, usually I use EQN to abbreviate equanimity. And here, an annotation. I use step 1 and 2 and equanimity. Now, another trivial one. This is again just the application of the Leibniz rule. If you have A is equivalent to B, then for a formula C and variable P, this entire formula is a gamma theorem. Why is it a gamma theorem? Because I can write a gamma proof for it, where gamma is, in this case, the singleton that contains one formula, one hypothesis, A is equivalent to B. At each step, I can write a hypothesis or an axiom. Here, in this case, we write a hypothesis. Step 2, now that the numerator of the rule of inference called Leibniz is written, I can write the denominator. Right? If A is equivalent to B in any formula C, you plug in A or B instead of your P, you get equivalent formulas. That's what this formula is. Any questions? All right, more axioms. Now let's prove something slightly less trivial. Prove that if A is equivalent to B and B is equivalent to C, then A is equivalent to C. Note that I read it a little bit differently, but this is basically saying that if I have two hypotheses, A is equivalent to B and B equivalent to C, then I can prove A is equivalent to C. Now, how do we prove this? Step 1, I can write any hypothesis. I write our first hypothesis. I annotate here that this is the hypothesis. Step 2, I can write again any hypothesis. I'll write our second hypothesis. B is equivalent to C is a hypothesis. Now I don't have more hypotheses, so I better get creative. How do I get A is equivalent to C. Yes. We don't. Where's the transitive property? We don't have it yet. We haven't proved it. We want to prove it. Is the transitive property an axiom? Wasn't, as far as I remember. Yes, it wasn't a rule of inference. We had two rules of inferences called Leibniz and axiom. So Leibniz and equanimity. So transitive property is neither of those. We don't have it. How do we do this? So we have to get creative. And here I'm going to use, to get to A is equivalent to C, using Leibniz. But Leibniz here, you see, it tells you that for any formula C, if I know A is equivalent to B, then I could plug in A or B instead of variable C. But if I pick this C, this for any formula C, if I pick this C in a clever way, that would, this bottom, because the result of substitution on one side gives me A and the other side gives me C, then we are done. Then I can get this. But so how do I choose C? Well, this might get tricky. Let me, actually, I don't know how to choose it yet, but let me see. So what if I picked, so I want to use, I can use either of these two. I don't know if I want to use as the numerator. Let's pick A is equivalent to B as the numerator. Now here, let me take, sorry, let me think a little. My C, I want my C to be, if I take A is equivalent to P, and if I, instead of P, I get A equivalent to A is equivalent to A equivalent to, yeah, okay. So maybe why don't I use this? A is equal, I will get A equivalent to B is equivalent to, yes. Yes, this will work. All right. Now I want to use this number 2. I know I have it, this hypothesis, and it's already written. Now the formula C that I want to choose in Leibniz, again, I repeat that this Leibniz is true for any instance of C, any variable P that I want. So I take a variable P, which is a fresh variable. It doesn't occur in A, B, or C. All right, so P is a fresh variable. I.e., it does not occur in A, B, and A or B or C. Note that when I said the C of Leibniz, I'm not referring to the C. That C was the general template, right? Now the C part of the Leibniz is this formula, right? The Leibniz was the formula that A equivalent to B implies the denominator for any C. Now here I'm applying it for when I have B is equivalent to C. Now here this C is a different thing. Let's call it D this time, so it's not confusing. But it's not going. I'm not going to take D. I'm going to take the formula. I mean, I want to take it to be a formula that is helpful, and I wanted that formula to be A is equivalent to B. But then what do I get? So I know B is equivalent to C. So in any formula, I can plug in B or C instead of a variable, and Leibniz is going to give me equivalent formulas. Now I pick this formula. Now in this formula, if I plug in P, B for P, it's equivalent to, when I plug into this formula, C for P. So this is equivalent to this. This is a Leibniz, right? This is an instance of my rule of inference, Leibniz. I pick the formula. If I know B is equivalent to C in any formula, in this case, that formula is this. A is equivalent to P. If I plug in B or C, I get equivalent formulas. With this, I get this formula. Now, what are the results of these substitutions? What is this substitution? Can anyone tell me what is this formula? In the formula, A is equivalent to P. Replace P with B. What do I get? A is equivalent to B. Now, how about this one? A is equivalent to C. Thank you. So this is the resulting formula. So this formula is the same as the denominator. The denominator is the same formula. So at step 3, finally, because the formula B is equivalent to C is written, I can write the result of the Leibniz, which is A is equivalent to B is equivalent to A is equivalent to C. Now, I'll write the brackets here so that we know these two formulas are equivalent. Now, how do I annotate this? You need to be careful. We use step 2. So step 2, I'm going to write it as the numerator. And then we applied Leibniz. Now, I want to tell you what exactly I took as the C part of my Leibniz, as this formula, right? Because this was the key information is that for the C of the Leibniz, template of Leibniz, I took A is equivalent to B so that you know how we got here. So I annotate here that the C part of the Leibniz is the formula A is equivalent to P. Now, another very key important thing is that this P wasn't just any variable. It was what we call a fresh variable. Why is it important so that it's fresh? Why couldn't I just take any variable? Because if P wasn't fresh, meaning if P occurred in the, let's say, formula A. Let's say formula A was P or Q. So P occurs there. Then the result of the substitution is going to change A, right? Because you're substituting P, and if A is P or Q is equivalent to P, in this formula, if you substitute P with B, then you get B or Q is equivalent to B, and this is not the same. Sorry, I wanted to change color. Not the same as A equivalent to P, A equivalent to B, which I wanted to get. So because I messed up the formula A here by choosing a variable that already occurs in A. So if P was in A, then I should have chosen another letter, another variable like R, S, T, right? So that the result of the substitution doesn't mess up A. Now, why don't I want to mess up A? Because we are not done yet, by the way. Now, how do I get to the formula that I want? Anyone? Any ideas? Yes. Exactly. Equanimity rule. Note that I have the formula A is equivalent to B, and the same formula equivalent to this. Instance of equanimity rule applied to this, that if I have the formula A is equivalent to B, and I know that A is equivalent to B is the equivalent to A is equivalent to C, then equanimity tells me, so let's call this A prime. Let's call this A prime equivalent to B prime, right? So I call this B prime, right? If you call this B prime, then this whole thing is A prime is equivalent to B prime, and equanimity tells me that I can get B prime. Therefore, I get A is equivalent to C as a result of equanimity from step 1 and 3. So here, equanimity, I need to tell you which steps I used. I used steps 1 and 3 as the numerator of the equanimity, or add EQ and 4 so that we know it's equanimity. Any questions? We are done. Why are we done? Because now we have shown that A is equivalent to C is a gamma theorem where gamma contains these two forms. Why is it a gamma theorem? Because it appears in a gamma proof. I wrote a gamma proof, a proof that uses only hypothesis from a given hypothesis from the set that I call gamma. All right, we're going to write a lot of gamma proofs. So if you're not sure about the steps here, I'm going to be sure now. In the remarks, I just explained the same thing about the that I explained about Leibniz. So let's move on to the next theorem. Now this one is an absolute theorem, meaning I'm going to prove it using no hypothesis, with the hypothesis the empty set. So this is saying that A is equivalent to A is an absolute theorem, meaning it can be proved without any hypothesis. So how do I prove this? Now I don't have any hypothesis to write. That's step 1. So what do? Well, I still have axioms. So why don't we start with one of the axioms called the idempotency of conjunction. I annotate here, I call the axiom idempotency of the or disjunction. Now, again, we're going to use one of our rules of inference. Which one should I use? There are actually, for this one, I think there are different ways to do it. And for these proofs are not unique. You're going to see that you can prove theorems in many different ways using different axioms, different steps. But in this case, I think the easiest way is to apply Leibniz. But how again? Note that I have now an equivalence that I want to take as the numerator of my Leibniz. That means in any formula C, if I replace a variable P with A, or just A, I'll get equivalent formulas. But the point is, for which C that's going to help me. Now, in this case, what if I take the C to be formula P? Just P, where P is a fresh variable. Again, it's important that P does not occur in A here for the purpose that I want. So I picked C part of the Leibniz to be the formula P. Now what happens if I sorry, let me see. This is not going to give me, no. What do I want? I don't want P, get A or A, and then get X equivalent to A. No, sorry. I just cheated. I need to take it A, obviously. Yeah. The C is A. Yeah, I don't know why I thought. Because that's going to give me the same thing. A or A is equivalent to A. We get formula to be A. Now, if P does not occur, P is fresh. Now you're going to see why this is very important to take this to be fresh, meaning does not occur. P does not occur in A. Now, if I plugged in A or A, the formula is equivalent to if in the formula A, if I plugged in A. Now, what is this? Now, note that P does not occur in A. We proved this, that if the formula A does not have any P in it, now you substitute P in that formula A with something. It's not going to change anything because P is not in A. There's no substitution. So the result of this is A. This one is also A. In the formula A, substitute variable P with A, where the variable P does not even occur in A. The result is just A. We proved this by induction, by the way. So the resulting formula is A is equivalent to A. And A is equivalent to A, it must be an absolute theorem. And this is how you prove it. I'll just annotate here. I used step 1, where I applied Leibniz. And what did I take as the C part of the Leibniz? The C formula here was A. So that you know how you get there. And it was important that P is a fresh variable. So we're usually going to write this P is fresh. Anytime you want to apply Leibniz, you want to take a fresh variable, because if P wasn't fresh, meaning if P occurred in A, then the result of this is not going to be A. So you don't get there. So if P already occurred in A, then pick another variable, Q. It must be fresh. If P was also there, if Q was also there, then pick another one, R. You need to take a fresh variable. And here we're done, because A is equivalent to A appears in a gamma proof where gamma is the empty set. That means it appeared in an empty set proof, meaning it's an absolute theorem. And here again, I remarked, I said the same thing about explained the Leibniz step here. I'll stop here. Next time, we are going to talk more about theorems and some meta theorems about the concept. Have a nice day, everyone. See you on Wednesday.